All right, I've got the top of the hour, and I want to welcome everybody to our webinar series, From Research to Implementation, that we do here at NCAT. It's a monthly webinar series. We try to do it the third Thursday of every month, and we have fantastic topics. It's always important for us to highlight the implementation side of the work that gets done in the asphalt industry. So this week, our topic is on improving OGFC durabilities and performance. And so we've got some great guests today. With us, as always, is Nathan Moore. He's an assistant director for the test track research here at the National Center for Asphalt Technology. He's responsible for seeing all of the test track operations and research programs. Prior to that role, Nathan was an NCAT lab engineer, and he specialized in balance mix design and friction testing. He holds both a bachelor's and a master's degree from Auburn University in civil engineering, and he's a licensed professional engineer in Alabama and the father of three very active, fantastic children. Dr. Chen Chen is with us, also known as Chen Squared at times. He gained his PhD here at NCAT and through Auburn University in civil engineering and earned both his BS and his master's degree from Chongqing Jiaotong University. He's currently an assistant research professor at the National Center for Asphalt Technology here at NCAT, where his research focuses on asphalt material performance, aging, and the use of recycled and innovative materials. Prior to coming back to NCAT, Chen gained valuable experience as an HMA lab engineer at Colas, bringing a strong implementation-focused perspective to his applied research, which is very important to us. And we love having Chen Chen back in the NCAT family and here with us often. We also have today with us Jim Musselman. Jim is the state asphalt materials engineer for the Florida Department of Transportation. He's worked in the area of asphalt pavement materials and construction for over 40 years. I didn't think he was that old, but that's what he told
I'm
me.
a lot younger in real
He
life.
said 40 years. So with previous position here at NCAT with us as a senior engineer and as an asphalt performance manager for CRH America's Material, Jim has both a bachelor's and a master's degree from the University of Florida. Go Gators, I guess that says. Yeah. That's odd. And he's a registered professional engineer in Florida. So a couple reminders for those of you that are here all the time. We ask that you keep yourselves muted the entire time during the webinar. And any questions that you have, we would love for you to put in the chat box. I'm going to go ahead and push that up to you guys and remind you the chat box is the best place for those questions. And we will get to those questions at the very end of the presentations. So given that, Nathan, I want to turn time to you.
Great. Yeah, I just want to reiterate what Travis said. I think we do have a lot of first-time participants. So first of all, welcome. Happy New Year. We are thrilled to have everybody on this webinar today. If you have questions, comments, anything like that, go ahead and get them in the chat as you're thinking about them. Some of them may be simple, and one of the presenters we can answer it quickly, or if it sort of sparks discussion, we'll hold it to the end. But it's really helpful for us to kind of pace and know sort of what our audience is feeling. So with that, also one final note on Chen's bio is he is an extraordinary cook. So you need to put that on your bio in the future. All right, let's go ahead and get started. I'm really excited to kick off the 2026 season of implementation webinars with our good friend Jim. Both used to be a part of our team at NCAT, but also just been a long friend of NCAT at the Florida DOT, with a topic near and dear to his heart. So many of you know the drill, but those of you who don't, here's sort of our schedule. I'm going to give a very brief introduction. Nobody's really on these calls to hear me talk. Introduction to the topic, then I'll kick it over to the NCAT subject matter expert, in this case that's Chen Chen on open graded friction courses, and then we'll hear somebody from industry or agency, and then we'll kind of go to questions. So history of OGFC on the test track. The very first test track was constructed in 2000, and we actually had 4 OGFC sections that were placed on that track in the West Curve. we evaluated things that you would typically think, would be necessary. So obviously constructability and things like that, but texture and friction and spray. And I actually pulled these pictures here from the original report from the 2000 after the 2000 cycle, looking at truck spray, water spray compared on open graded friction courses to dense graded. I'll never forget. I was driving with my wife one time. On the interstate, and there was some new construction, and they hadn't put an OGFC layer down on I-65 in Alabama. And so we're driving, and then all of a sudden we go from OGFC to dense grader SMA, and I got really excited, and I interrupted my wife, and I was like, "Did you see the difference in truck spray in the truck in front of us?" And she didn't care. But nonetheless, I think these are great pictures, even though they're at this point 25 years old. I think it tells a great story. Um, so lessons learned over the years, and this was really going to tee off Chin to talk about some of the research that he's done, and then also Jim to see what Florida DOT has done over a quarter century. Um, Binder quality and tack quality matter. I think that kind of goes without saying, but binder quality, binder quantity, and tack matter, and we've got lots of information to show on that to improve durability. You don't want your mix to ravel, and you definitely don't want it to debond. There was some work that we have done for ALDOT demonstrating that there is actually a slight structural benefit from OGFC, although most agencies don't implement or utilize OGFCs for any structural benefit. But some work that Dave Tim did years back demonstrated that you could probably get a structural coefficient if you want to think in terms of AASHTO 93 layer coefficients. You can get a structural coefficient of about 0.15. So it's not a ton, but it gives you a little bit of a bump. But the one that I'm really most excited about, and I think it tees off our other presenters today, is the idea of the trade-off between durability and permeability. Many people on this call are probably familiar with the concepts of balanced mix design, where you're balancing different modes of distress, typically rutting and cracking, where you give a little bit of one to get a little bit of the other. And OGFC durability and permeability are no different. The more binder you put into the mix, the better the durability, and you reduce the risk of raveling. However, you begin to fill those voids up that are necessary for permeability. You fill those up with binder. So there is a trade-off. And one of the most exciting things that I think I've seen data from the track is what I'm showing you here. And Jim will talk more about this later, but it's some work we actually did for the Alabama Department of Transportation about a decade ago at this point, where we built two mixes, and that's the red and the blue lines. I think hopefully you can see my mouse. The red and the blue lines here that are basically tracking along each other. Those are 12.5 nominal max aggregate size. One of them had aramid fiber. The other one had, I think, like GTR or asphalt rubber binder. But then we also made an OGFC mix out of 9.5 millimeter nominal max aggregate size, which is finer than OGFC is you would see typically. And what I want you to see is permeability started off. This is permeability. It started off lower than the original, but then it decayed significantly slower, where you actually had about double the permeability life on the 9.5 OGFC layer compared to the 12.5. And I think this was a really novel idea that ultimately you're going to see kind of, Florida saw stuff like this in their own work, and they actually have begun to implement it. So I don't really want to steal anybody's thunder. And so with that, I do want to kick it over to Chin, and let's hear what he has to say. So Chin, I'm going to stop sharing.
So as Nathan mentioned earlier, we NCAT Test Track did a lot of study on OGFC, and also NCAT Lab, we did a lot of study OGF study, I mean, for different DOTs, especially for Florida DOTs. So today I would Nathan mentioned, so the binder quality metric and also the 9.5 gradation will help. So from the permitting side. So one of the study we did for the Florida DOT is OGFC suitable for suburban environment here. So today I'm trying to introduce part of the study related to the topic here, like using a final gradation, what will happen. Mm, So, I think both Nathan already gave like a very good introduction about what OGFC is. So in typically OGFC compared with dense grid mixtures has like much higher air void, or about 15 to 22% air void, typically composed primarily of a single size coarse aggregate and use modified binder and fiber to, for the stabilization purpose. The benefits, and Nathan showed very good pictures to reduce noise, reduce the hydroplaning spree, and to improve the safety and visibility. So this is like the benefit of why we want to use OGFC. So that's the pretty quick introduction about OGFC. And but we also have a challenge. And for the OGFC, the biggest challenge, NCAT did like a survey among different contract and duties, and we found the biggest challenge for the OGFC is the early failure, the premature failure, which is raveling. And in general, it doesn't last as long as like dense grid mixtures. So we have like raveling, cracking, stripping, clogging, and delamination. I mentioned, but the raveling is a major concern for the users. So typically, the raveling is the material damage. Okay, so it's not a structure damage. It's like a material damage. So it's like caused by can cause by like moisture damage, insufficient aggregate and binder bonding, and shearing force between tile and pavement. So from both inside and outside factors can affect. So the raveling is the biggest problems, and the cracking and texture, sometimes can be a concern, but a major concern, as you can see in this picture here, is the routing issues. So the particle is losing, so you are going to losing that like benefit, cause like the premature failure. So, I mean, OGFC is also called FC5 in Florida. So in Florida, in order to improve the safety, they require any payment the speed is bigger than 50 mile per hours. It is required to use OGFC or FC5. Typically, they place at like about 3/4 inch thick with no structure values. And typically, the FC5 is the M mass of FC5 is 12.5 millimeter. Binder is like a PG76 binder. So especially in the with expansion of Florida City, a lot of like suburban areas it have like high like high shear stress caused by like the stopping or the speed, and that stopping of the vehicle can cause like the raveling early failure of the OGFC, cause raveling. So that's why for the DOT did like some studies before, trying to say, hey, how we can improve the OGFC performance, especially in terms of durability, how we can make the OGFC life to become longer. So there's two studies did like part of their study indicate like, okay, when you are using a fine gradation 9.5 ms or high polymer modified binder, there's a chance. I mean, these two things can help to improve the durability of OGFC mixtures. So this is from the previous Florida DOT. We focus on these two studies because they study using the Florida materials to do the study. That's why we think these two things can be very important. So what we did for the FDOT BB15 project is, hey, we use two aggregate from Florida, which is the Florida limestone and Georgia granite, and we use two binders, 76 binder and high polymer binder. And we use like the pipeline method after sampling materials. For the DOT, use pipeline method to determine the preliminary binder content. Then we validate the binder content using air void and cannibal loss. Our requirement is the air void should be bigger than 15%, and the cannibal loss should be less than 20%. Okay, so after we done mid-design, we did a very comprehensive lab testing to compare, to evaluate the impact of hyperlink binder and 9.5 ms gradation. So the testing we include in this study is durability, we use Canterbury, and cracking resistance, we use overlay testing, writing and moisture damage, we use like Hamburg testing, the friction we use DFT, and permeability we use the Florida permeability test. So we trying to cover, the durability, cracking, writing, friction, permeability. We're trying to cover very comprehensive lab testing, trying to evaluate the impact of 9.5 millimeter MS gradation and the hyperlink binder. And this is the summary of MIG design. So based on the pipeline and the preliminary performance validation, as you can see, for the granite, so the FD5 and 9.5 OGFC, the end design is same, the bottom content is exactly the same, the airboard is exactly the same. So, but for limestone, the limestone, the bottom content, 9.5 OGFC is slightly higher than the FD5, but their airboard is pretty close. So in terms of bonding content and airboard level, they are pretty similar and comparable. Now we go to the performance side one by one. For the Canterbury loss result, as you can see here, the arrow here indicates, lower number is better, okay? The y-axis is the Canterbury loss. Typically, our criteria is 20% here. And as you can see here, we have the granite without and limestone without. For the granite without, with the blue bars is the mixture prepared with 76 binder. The orange bars is prepared with high pollen binder. So in general, when we compare with 76 binder and high pollen binder, no matter which aggregate you are use, okay, as you can see here, and no matter which gradation you are using hyperlink binder will tremendously reduce the cannibal loss, which means using hyperlink binder will definitely help to improve the durability of OGFC mixtures a lot. Okay, now we compare with the gradation. If you compare, for example, for the granite, if you compare the FT5 and the 9.5 OGFC, from the lab result, as you can see, the number reduced, the cannibal loss reduced, which means the final gradation can improve the durability. Okay, remember I showed you earlier, they have same bond content and same airborne level, but the cannibal loss just reduced. And the same trend we found on the limestone OGFC design. So when you're using high polymer binder, it's going to help a lot. When you're using 9.5 OGFC gradation, it also help. But very interesting things here, when you are using high polymer binder, the number is continually slow. So it doesn't mean the gradation doesn't help. It's the performance is dominated by the high polymer binder that way. So that's why when you use 76 binder, you can see the benefit of final gradation or 9.5 millimeter MS gradation here. Next, we are talking about the overlay test result. So, in again, the area here show the lower CPI number. CPI indicate cracking propagation rate. Lower number, better cracking resistance. So again, when we compare PG76 binder with high polymer, we can see clearly when you use high polymer binder, the cracking resistance is better. And when you are using a final gradation, they are comparable or slightly improved, but that's not that much. But at least we can make a conclusion here. When you are using hyperlink binder, the cracking resistance of OGFC mixture will increase, will be better. When you are using 9.5 millimeter MS gradation, the cracking resistance will be maintained to be comparable. And that's what we thought here. And for the Hamburg test result here, the writing resistance here, as we know, no matter which binder, which gradation you are using, or which aggregate you are using, no stripping would happen during the testing result. And if we compare the write depths, they are pretty similar. So it looks like, it doesn't matter okay, it looks like in the high polymer binder and the final gradation don't affect the writing resistance, but that's not the case because we know the OGFC have the stone-to-stone structure, stone-to-stone contact structure. In that case, the aggregate structure provides excellent writing resistance. So in this case, the stone-to-stone contact ensure the writing resistance. So it already have very good writing resistance. Now, when you use the final gradation or hyperlink binder, it doesn't obvious the impact of these two things doesn't show here, but doesn't mean it doesn't help. So that's why when you use OGFC, when you do a good design, the stone-to-stone contact will be dominate the writing resistance here. And one thing we care about is the friction. So the arrow means higher number is better. So as we can see here, clearly see like the binder doesn't affect the friction, which is expected. Okay, so the aggregate quality and aggregate structure control the friction, not the binder. So we can find the trend here. But when we move into a smaller, when we like using like 9.5 OGFC here, as you can see, like hey, the friction either keep consistent or slightly increased. So again, similar with the cracking, when you are using 9.5 millimeter MS, so the friction properties maintain comparable or slightly increase. Generally, they are comparable. Donor. So using 9.5 millimeter MS gradation doesn't hurt the friction and the cracking. Actually maintain the same level or slightly increase. The last thing we're talking about is the permeability, because we care about permeability. If the permeability is not qualified, that's gonna be disaster. So Nathan will not have a chance to be excited to tell his wife, hey, to see the difference. So the permeability number is higher the better. So in general, we can say, in general, when you change the binder, the permeability will not change, will not be affected, which is also expected because the air void level control the permeability. So change the binder source will not actually change the permeability. But when you change to the 9.5 millimeter gradation, as you can see here, well, it's pretty comparable. Compare with different when compare with from 50, 52, 50, 51, and 73, 64, 75, 71, they are pretty comparable. So like again, we don't see like a drop when we switch to the 9.5 millimeter gradation. So that's from the lab side. Okay. So Nathan showed a very good picture. I'm also showing here. We don't communicate before that, but we just like, I think both of us are excited about this slide because what we found is very exciting for us. As you can see here, so we have three OGFC mixture from L dot sections. So the green and the red is, I mean, the green and the red sections are 12.5 millimeter OGFC. And you can say, both three OGFC mixtures have very similar like, beginning permeability. Maybe the E10 have like slightly lower number, but at first beginning, the number is pretty high. But as you can see, for 12.5 millimeter, for like a 12.5 millimeter OGFC, it dropped very quickly. For example, after about one like 1.5 years here or 1 year here, it only drop here. So in order to drop to the same level, the 9.5 OGFC here, it take about like 3.5 year or like 4 year. So no matter the reduce of the permeability is caused by the traffic or caused by the clogging, so that's as you can see here, when you are using a 9.5 millimeter OGFC, it can extend the permeability life tremendously. Okay, so when you drop into after about like 4.5 years, the 9.5 millimeter OGFC still have about 50 meter per day permeability. That's like the minimum threshold. But For 12.5 millimeter OGFC, after like 1.5 years, it's there. So, but that's on the test track, accelerated traffic. Okay, so that doesn't mean in the like real highway. But again, you can say using 9.5 millimeter OGFC can extend the permitted life of OGFC mixtures. So this is a quick summary table to show like when you are using 9.5 millimeter mass gradation and hyperlink bundle, what will happen? For it's very like easy to understand. The green area up means like improving, and the orange flat means like comparable or very similar. So if we see the first column here, when you are using 9.5 millimeter MS, you are going to improve your durability and form the lab-wise to have a comparable permeability. But when the field-wise, the permeability will be extended. So I put improve here. But we'll have a comparable cracking, writing, and friction properties here. When you are using high polymer binder, you're going to improve the durability, improve the cracking, will not affect the friction permeability. That's obvious. But high polymer binder doesn't improve the writing resistance. Doesn't mean high polymer doesn't do the job. It's only mean like for OGFC, the stone-to-stone contact dominate the writing resistance of its mixtures. So even use a very good binder there, it's not going to show the benefit. But again, high polymer binder, if you use in the discrete mixtures, it definitely will show the benefit. So here, so it's like a very quick introduction about my section. Then here I will handle to Jim. Jim is going to talk about the implementation of 9.5 millimeter OGFC here in Florida.
Excellent, excellent. So, and it's been a bit of an evolutionary cycle, and I'm gonna, bear with me. I'm gonna go through a little bit of the history of how we've used it, but then touch on some of the changes that we've made through the years. So, just to give you some background information about Florida, overall, the whole roadway network in Florida, there's over 275,000 lane miles in Florida, and that includes like the state highway system, county road system, and local roads. But the state highway system, that's the part that belongs kind of to the Florida DOT. We have the interstate highways, US highways, state roads, and toll roads and expressways. So the one thing you'll notice, we don't handle the county roads or local roads. So we're mainly dealing with a higher volume system. Okay, on our system of that 46,000 lane miles, you can see the breakdown between interstates, arterial, and then the turnpike. And roughly 97, 98% of it is asphalt, and then the remainder is concrete. Of those asphalt pavement surfaces on the state highway system, it's almost a 50-50 blend of open graded surfaces and dense graded surfaces. So we put down a lot of both every year, and we have different criteria for it, which I'll get into later. So if you're not familiar with open graded friction courses, number one, you're probably saying, why are you watching this webinar? No, but basically it's a special type of asphalt surface mixture, and it's basically designed to improve safety. It lets the water pass through somewhat through the top surface layer. If you look at the slide on the picture on the right-hand side, you can see this is about a 1-inch layer of an open graded mix. This is a dense graded super paved mix below it. And it's primarily composed of coarse aggregate. So you end up having a larger percentage of air voids. These are designed somewhere in the, let's just say 15 to 20% voids compared to a dense graded mix in Florida, which would be designed at 4% voids. And in Florida, we use open graded friction courses on high-speed multi-lane roadways to basically reduce the risk of hydroplaning, as well as improve the visibility when it is raining. And we'll talk about the rain a little bit later. But in Florida, the open graded friction course, as you may have picked up from Chen's presentation, is called FC5, and we have a new one that's called FC7. And I won't confuse you with how our nomenclature works for the naming convention. So again, here's a typical shot. Open graded mixes, when they're produced and placed properly, they're gorgeous mixes when you put them down. They're very black, they're very rich looking. This is an older one. This was in North Florida. This actually was one of our first polymer jobs where we started using it in open graded mixes. And if you zoom in, you can kind of see that surface texture. You can always tell a DOT person took the picture because there's a penny out there. So, and actually, I think I took the picture and I found the penny on the project. So it's kind of interesting. Our use of open graded friction courses, it kind of goes back to 1966. And just those of you take Cape and Count at home in 1966, I think I was in second grade. But basically, that it was the Highway Safety Act. It was a federal law that was passed, and it required states to develop standards for pavement design and construction with specific provisions for high skid resistant qualities. So that's kind of where it all started. Prior to that, it was just the Wild West when it came to pavement surfaces, at least in Florida. They weren't really too worried about pavement friction or hydroplaning or anything like that. So in the late 60s, DOT evaluated a bunch of different aggregates and different test sections. And ultimately, we came up with different types of friction courses. So this is like a timeline. I won't bore you with the details, but it started back in 1966. We used wearing courses for a while. Then we used something called an FC2. An FC2 was a 9.5 millimeter nominal maximum size mixture, but it used AC30. It didn't use any fibers. There was no modification. And the way we kept it from draining down was we used to produce it at around 230 degrees Fahrenheit. So it was kind of warm mix before warm mix was a thing. In the late 90s, we actually copied a friction course from the Georgia DOT, and we called that our FC5. And that was a 12.5 millimeter mix that had fibers. We used modified binder. We started off with asphalt rubber, and then we kind of morphed over to polymer modified. They have liquid anti-stripping additives, and also for certain aggregate types, we have high-graded lime. And now the FC7, which is going to be the new kit on the block, that'll be effective in the July letting this year. So it'll be a 9.5 millimeter mix with all the goodies, just like FC5 has. So we're looking forward to that mixture. So the general policies on the usage of open graded friction courses, so they're used on high-speed arterials and high-speed limited access multi-lane roadways with a design speed of 55 miles an hour or greater. Chen, I think in his presentation showed 50, but that was a recent change that the department made. So we bumped it from the design speed from 50 up to 55 miles an hour. And again, as I mentioned previously, about 50% of our system are open graded friction courses. And we use it primarily, it's a safety feature, and we're really very pleased with it. And the downside of open graded friction courses is we have a shorter life. In Florida, we're blessed with generally warmer weather. We don't have a whole lot of freeze thaw. So we typically get on average about 14 years out of our open graded friction courses. And then when they give up the ghost, they're going to deteriorate by raveling. So it might be 17 years old, it's going to ravel. It might be 8 years old, it's going to ravel. Again, when it comes to safety, this kind of gives you an idea that you can see in the panhandle, we're more than 64 inches a year. And then the rest of the state, you can kind of look at the map yourself, but we get a lot of rain in Florida, and it's not these nice little slow rain for a day or two. It's like a thunderstorm where it's, 3 or 4 inches an hour for 30 minutes. So we get a lot of water buildup. So that safety is an issue. This was a study that was done in Japan about 13 years ago, where they went out and they looked at 213 different areas they were prone to having wet weather accidents. And so they had dense graded mixes that they put. And I think what they did is they looked at it from the number of accidents from 1 year before they actually did the construction to 1 year afterwards, and compared those to see, hey, how did they do? And there was a significant decrease in the number of wet weather accidents. So again, it just kind of further reinforced the benefits of open graded friction course. This is something, and I didn't give this picture credit, but I got it from Don Watson. So Nathan, the one that you've got, and something tells me that this was a TxDOT picture. So again, whoever's picture it is, thank you for letting me use it. Hopefully we won't get sued. Anyway, so, but you can see there is a reduction in splash and spray. Now, one thing open graded mixes with time, they will close up. They don't close up like a dense graded mix, but sometimes you'll drive through a job and there's considerable splash and spray. So they don't maintain that nice brand new open texture forever. as I mentioned before, performance can be an issue with open graded mixes. They're safer, but their long-term performance just isn't really quite as good. And so in Florida, we typically get on average 14 years out of our open graded mixes, 17 years out of our dense graded mixes. So you can kind of see these charts here, and keep in mind, it's an average. So there's a certain standard deviation associated with it. So we have some for open graded friction courses that maybe they start to give up the ghost after 8 to 10 years. And maybe we have some that last 16, 17, 18 years. So again, there is a distribution on it to where you see it. Now, this came from an earlier test track report where you can see what NCAT asked agencies. They took a survey to see what is the typical service life of your open graded mixes. And, the majority of them were in the 8 to 10 range. I think we were probably in this group here. And again, part of it is, we've got pretty good weather for open graded mixes compared to a lot of other states. So you could see typical service life around 8 to 10 years. And in Florida, that's a little bit of a problem if, like, even with 14 years where the underlying pavement layer, we get 17 years. What do you do? Because it's starting to ravel up after 14 years. And so we don't want to impede the public any more than we have to. So we'll typically do the full milling and resurfacing at 14 or 15 years rather than getting out to 17, 18 years and doing it. So anything that we can extend the life of the pavement would have a significant impact on our program. Again, raveling is a big problem. A lot of times we see raveling, and this is something I learned from Buzz Powell when I was at NCAT. You will typically see a lot of the raveling that occurs anywhere you may have a cold joint. Okay. And the reason for it is you start paving, you're starting to pull, the paver's cold, everything is cold. And as you're paving that mix, it's losing temperature as it's going through the shuttle buggy or going through the paver. So that's kind of where we see it a lot, but we'll also see it in other places. And sometimes it could be a construction thing, could be a mix design thing, could be we didn't tack properly, we didn't broom properly. A lot of things can cause raveling. One of the things that's I think it's unique to Florida, which is this isn't the gist of my topic, but this is something I think we should talk about some more later on, is we have a laser crack measuring system that is really good it can really give us a good overview of the pavement. So these are very expensive. I think each unit is over $1 million, and it gives you a downward looking image that is very, very detailed. And they can analyze the pixels, and we can essentially quantify raveling. Prior to this, we would just go out and there would be, the pavement condition survey operators would just note that there was raveling on the project, whether it was low, moderate, or severe, but we had no way to come up with to quantify that data. Well, now we have, and so they run these reports. This is a Power BI report that's accessible. It's an internal report. It's got a lot of stuff on here, so don't get too misled by it, but it'll locate every single area that has some raveling. So it could be a 2-foot area that is raveled on a project, and you can see the graph on the right, that looks like a mess. But it can also characterize it. So you can see we had 1,200 lane miles of low raveling, 200 miles of moderate raveling. Fortunately, only about 11 or 12 miles are severe raveling. And if we take this down and drill down a little bit further, because again, it's hard to, at that resolution of the map, it's hard to tell, but if you zoom in a little closer, this is the Tampa area. And I know it's really hard to see, but if you squint your eyes and pretend, so this is I-4 coming through the area, and it turns into here, and it becomes, here's I-4 coming down. It turns into I-275. You see very little. There's like a little bit of raveling on, again, limited access is not all that much. But if you look closer, and I'm not sure, this is an arterial, but you see all these little dots. So the red ones are severe, the yellow ones are moderate. And you can see all the arterials, we have a good bit of raveling on the arterials. So it does appear that we're having more of the raveling problem occurring on arterials. And that kind of led to a certain extent about why we did the project about open graded friction courses in suburban areas. So, so the way we design open graded friction courses is also something that's, kind of a little bit unique. we need to have enough asphalt binder in the mixture for good durability. But on the other hand, if we put too much binder, it can create construction problems. We can have drain down or bleeding, or it will tend to fill up the pavement structure with time under traffic, which you see on the bottom here, or it can do both. You can have a drain down problem, and then later on you lose all your texture. So we're always kind of careful about it. And it's a little bit of a balancing act, like everything else we do in the asphalt world. Wouldn't it be nice if we could just, hey, we change this and we fix all of our problems? But years ago, back in the 80s, everybody had rutting problems, and we did stuff to fix rutting, and that's great. We fixed all the rutting. Well, now we have cracking. So everything that we do is a pendulum, and open graded friction courses are the same. And to a certain extent, you're balancing performance and safety. If you have more binder in the mix, it's going to improve the performance, but it's going to reduce safety. Less binder, you're going to improve the safety, but you're going to have worse performance. So that's always a challenge that we all face in the asphalt world with pretty much every decision we make. The way we design, I'm not going to bore you with the details on it, but it's pretty primitive the way we design open graded friction courses. We have taken it and tried to bring it into the 21st century, but it was loosely based on a 1990 FHWA design procedure. They had issued a technical advisory where essentially you use pie plates. So you take Pyrex pie plates, mix the asphalt with the aggregate, put it in the pie plate, and try to set the optimum from looking at the bottom of the pie plate. And then what we do in Florida is we set the optimum binder content, and then we verify that with the Cantabro test, which we kind of consider a performance test related to durability. So here's some pictures. So these are the pie plates at 3 different binder contents. Let's just say whatever, 5, 5.5, or 6, or excuse me, let's say 5.5, 6, 6.5. And you'll get a good close-up view of the bottom of it. And what we're looking at is what part of the area of this is kind of coated with asphalt. So in essence, the asphalt's kind of draining down off of the aggregate. And then once we come up with an optimum, and it's a very subjective test. So right now, I think Travis mentioned Greg Scholler. He's our bituminous engineer, and Greg, he puts his eyeball on every one of these, and he'll actually sometimes invite me out and other folks in the lab as well to try to identify what do we all think the optimum is on this mix, because it is so critical. Then once we do is, we'll run Cantabro tests. If you're not familiar with a Cantabro test, it's basically you make a gyratory specimen, put it in the LA abrasion machine for something like, I don't know, I'm guessing 300 revolutions, and you weigh it before and after, and you look at the loss. We also have the capability to run drain down tests, but we rarely have any problems with actual drain down, so that's not run very frequently. One of the things we've been looking at is try to, rather than rely on Greg's eyeballs, because he's close to retirement, as am I, that we don't want to leave it so that it's subjective. So we're trying to use machine learning. We've got a program where we have an imaging system. So we take the pie plate, you can see it right over there, and then we image it, and it'll do the analysis. And basically the machine comes up with what it thinks the optimum binder content. And we're still in the process of calibrating it, but for the most part, it works out really good. Folks in the lab refer to the machine as Rosie. Remember, Rosie was the robot on the Jetsons back in the 50s and 60s. And so we call it Rosie based on the robot. So again, that kind of led to this project that we had with open graded friction courses for suburban environments that NCAT did, which kind of basically propelled us into making changes to our program. And again, this is a slide, and I don't recall, Chen, if you covered this, but again, using the high polymer, and I know a couple folks had questions about what a high polymer was, and that's in the chat, but we basically use multiple stress creep recovery specifications to define what high polymer is. Other parts of the country might call that HIMA binder, but we kind of felt like HIMA was a proprietary name and we wanted to be a little bit more generic. So we call it HP or high polymer, but it's essentially HIMA. And so you could see that the 2 pluses means that it really did improve. So high polymer would be pretty good. Now, one thing with high polymer is it's an expensive binder. It's probably $200 per ton of liquid more so than our conventional PG 76 minus 22. And the 76 minus 22 in Florida is $150 a ton more than unmodified binder. So basically, high polymer binder is $350, $400 per liquid ton more so than unmodified binder. So it's an expensive thing. So we looked pretty seriously at the 9.5 millimeter mix because it helped durability a little bit, but it didn't necessarily have a negative impact on the other things, particularly permeability and drainability. Okay. So we're in Florida, we're calling that the new FC7. And basically, if you want to know, it's the 7th friction course that we ever have used in the state of Florida. So it's a 9.5 millimeter nominal maximum aggregate size. We've got cellulose stabilizing fibers in it, 76 minus 22 binder. In certain areas, we will use high polymer binder if it's an urbanized area where we're going to have a lot of turning movements that are really prone to raveling. We'll recommend that they use it on those if the district can afford it. They'll include liquid anti-stripping additives as well as hydrated lime. Now we'll add 1% hydrated lime for typical Georgia granite mixes, but in Florida, we have always got aggregate shortages. We get a lot of aggregate coming down from Nova Scotia, Canada, and other provinces within Canada. But if we have Canadian granite, we actually use 1.5% hydrated lime. And again, this was a recommendation from a previous study that we did with NCAT. Our mixes, as Chen mentions, they're going to be placed. They're going to be placed 3/4 of an inch thick. And what we've seen is we've got pretty much improved Cantabro results. With FC5, we would normally get somewhere around a 14% loss. And with FC7, that number's dropped below 10. And right now we're thinking it's around 9. We do have lower permeabilities. And so far, we've only used it on a couple projects. But again, going back to our old FC2, there's nothing unique about a 9.5 millimeter open graded mix. It isn't like, hey, we're going from super paved to SMA or something that's really tricky. There shouldn't be any changes in the production and placement of these mixes. We have an asphalt test road that's north of Gainesville that we constructed a couple years ago where we have different test sections under real live traffic. And again, this is the FC5. You could kind of see the information on it. This is actual lock wheel friction testing that we did. And the permeability, let's just say 58,000. This is the FC7. Again, 6.3% binder versus 6.8. Again, finer mix, but it's got a higher binder content. Permeability around 34,000. So just real quickly, some of the changes. In 2000, we adopted Georgia DOT's demodified mixture. And we called that FC5, and that kind of helped our performance. We made some changes to our design guidelines that prohibited the use of open graded friction course mixes in turnouts, crossovers, and other areas. So we don't put them in those areas anymore. 2013, we bumped up the binder content. We made it a concerted effort to add an additional 0.5% of binder if possible. 2016, we started running the Cantabro test. Again, some of these were based on recommendation. I think it might have been Rutgers University that made that recommendation. We also eliminated the use of open graded friction courses and curb and gutter roadways. We've increased TAC coat, so it's gone from pretty low rate to 0.06 gallons per square yard. Started using polymer modified binders exclusively. We started using high polymer binders in urbanized areas that were prone to raveling. Started using both liquid anti-stripping additives and hydrated lime. Again, these mixes are just going to be kind of saturated with water. So you certainly want to have a good bond between that aggregate and the binder. And then we modified the gradation band. At one point, it was maybe some mixes were a little bit too coarse. And then most recently, we developed the FC7. And our current status is right now, open graded friction courses are required on all high-speed, multi-lane arterials and limited access. And we define high speed as a design speed of 55 miles an hour or greater. And we're going to continue to use it on the FC5 will be on primarily interstates and turnpike limited access. And it's the district's option to use either FC5 or FC7 based on where the location of the project. But on our arterials, we trying to recommend to use FC7, but there are some situations where maybe the speeds are too high and we still stick with FC5. So that's all I have for you. And we'll be glad to, I'll turn it back over to Nathan.
For the attendees online, the recording of this webinar will be available in about a week on the NCAT website. So if there's anything that was discussed that maybe you missed or you would like to hear again, it's a great place to do that. So I'm just going to summarize the two presentations we heard, and so with some couple recommendations, and then we'll get to Q&A. We heard both Chin and Jim talk a lot about raveling. Raveling is generally considered the most prevalent distress in OGFC. Delamination and cracking were also mentioned, stripping, but raveling is by far and away the biggest concern. And they talked about some ways to mitigate it, mitigating it with finer mixes that come with higher binder contents or high polymer binders. So I thought both presenters, you guys did a really nice job of sort of explaining, why you may want to use one of these versus the other. Jim, I liked your talk about raveling at cold joints. That's not really a mix quality issue. You can have an excellent the greatest OGFC mix of all time, but if it's too cold when you place it, you're going to have problems. Jim, you didn't mention this, but I believe it's the Tennessee DOT has actually implemented a policy where they will pay for the first load of waste material to go out to OGFC jobs on cold joints to heat everything up, and then so that your paving equipment is actually hot when you put the first load of OGFC down. I think that's a really elegantly simple solution to that problem. I can tell you from experience, you can almost every single cold joint on interstates with OGFC in Alabama have some form of distress. So I thought that was a really good point. I liked the method that Jim talked about, quantifying raveling, but also giving an indicator of severity because it's not all the same, and it can lead to better decision making from your pavement management folks and from an agency perspective. Not all cracking is the same, not all raveling is the same, and so using your automated stress vehicles to quantify this raveling in OGFC is great. I really like that. Both Chin and Jim kind of touched on it, but I did want to add one extra thing in here. You could see some of the work that honestly Chin and Jim did. Jim started the work with Alabama DOT whenever he was at NCAT, and then Chin kind of picked it up. But design mixes, we're big fans of designing mixes using BMD style testing. I think Florida has a very robust program talking about the pie plate method and with Greg's extensive experience. But for somebody who maybe doesn't have that kind of experience like the Florida DOT does, they're a little bit of a unicorn in that regard, where they have an ability to design high quality OGFC mixes because they've been doing the same method for a long time. But for folks who are maybe don't have that experience, we're a big fan of Contabro and air voids as sort of the seesaw, the trade-off between durability and permeability. And actually some work that NCAT did with Alabama DOT a couple of years ago was implemented into a new specification where that's actually part of ALDOT spec. It's minimum air void, minimum Contabro loss after a little bit of aging. But to close out, both of them talked about this. OGFC is a really great option to improve safety, whether just for friction in general, but also to reduce hydroplaning. So with that, I will open it up to Q&A, but I just want to say one more time, thank you to Chin and Jim. This was an excellent webinar. I learned a lot. This was really good. So I know we got a lot of questions coming in the chat. So Travis, I'm going to turn it over to you.
Okay, fantastic. I agree. That was great webinar. So one of the things that came up a couple times is the discussion about OGFCs used in cold weather climates or freeze thaw climates. And so, Jim, I realize you don't have a lot of that where you are, but I assume that you've seen some of that. And I know there's been work done at Minroads using OGFCs in Minnesota, and there's been studies done out of Japan and studies done out of Europe, both using that. Do any of the three of you want to talk about the cold weather use of OGFCs?
Uh, Jim, do you want to go first?
No, go
Yeah,
ahead, Chen.
please, Chen.
Okay, yeah, I do. This is a very good questions. I think a few years ago, I think NCAT did a survey among DOT like, hey, did you use OGFC? History, yes or no? Why are you still use it or why you don't use it? So I think the survey answer from like several DOTs, they said like, yeah, we used to use OGFC in. It's like when talking about that, they are several northern states. So they are using OGFC. OGFC does provide, safety and, reduce the perm and reduce hydro planning, all the benefits they have. The issues is in that time when in the winter, they spray salt. When they use the salt in the winter, I mean, they don't say like after, I mean, at the first beginning, they are worried about, okay, after the freeze thaw cycles, the OGFC have much bigger, uh, much higher airborne, it may cause like extra damage. But based on my limited experience, I think they don't found that raveling or damage issue, but they do found when they use the salt after the whole winter, the salt is kind of like, clogging the system. The permeability reduce a lot.
Yep.
That's why they kind of like slowly, reduce to use OGFC. But there are some states that are still using OGFC. And talking about Europe and Japan, the winter time they use a lot of OGFC there, especially Netherlands and Japan. And the way they treat the way they trying to do that is that they do a double layer OGFC. In that case, it will help to prevent the clogging or at least to extend the permeability life. That's what based on my discussion with other research and papers I read. I hope that answers your question. And maybe Jim
Okay.
and Nathan, you can add on that. Yeah.
Nothing from me.
Yeah.
Okay. Okay, I know one of the keys to using OGFCs in those environments is having that proactive, robust maintenance in the winter. To know to pre-treat, to use a brine maybe instead of the actual salt itself, or some of those other ways to make sure that they can last. Another question that came in a couple times is kind of what is the definition of HP binder? And I appreciate Greg putting in some of the super technical stuff. But for some of us that don't want to live in the binder lab, uh, Jim, what do you say is the simple version there? Just that
Yeah,
90%
I would probably
recovery and
say a normal.
5%?
Yeah, I would say something along the lines. Again, my basic current definition of it would be a normal PG 76 minus 22 modified binder might have, say, 2 to 3% SBS polymer in it. This one is probably in the 5 to 7% SBS range. I think some states specify HYMA binders with a minimum percentage. We don't do that in Florida. We specify the massacre criteria, and if they meet that, they can use it. We only allow the particular SB or SBS polymers. We don't use rubber to modify for the high polymer mixes.
Okay, and you bounced right into the next topic that I wanted to talk about. There were several questions about why Florida has moved away from using rubber and have gone to the polymer modified binders. And do you want to take on that one?
Yeah, I'll be glad to. And so Florida, there was some legislation that was passed in the late 80s, and we started using ground tire rubber in pretty much all of our surface mixes, and did so for probably a good 10 years, from like 93 to 2003, 2004. Then we started to use more and more polymer modified binders. And what we found is that we were getting a lot of complaints from contractors that, hey, the rubber would settle in their storage tanks at the plant, which was a real pain in the neck to clean. We found that on jobs that were bid with using polymer, we're getting bid prices lower than if it had rubber in it. And then the third thing, when we did studies comparing polymer with rubber, the polymer outperformed. So there were less handling problems. We got better performance, and it costs less to use polymer than it did rubber. So ultimately, the DOT changed our specifications and said it was kind of market driven. So we have an SP or a PG 76 minus 22 PMA spec, and we have a PG 76 minus 22 ARB spec. And it's the contractor's choice. If they want to use rubber and it's cheaper, they can use it. They want to use polymer, but everybody is almost 100% using. I don't think we've used rubber in, I don't know, 5 to 8 years in Florida.
Okay. And back when that rubber was being used there, was it mostly being terminal blended, or was it being blended at the plant?
Yeah, it was basically it wasn't. There's weird definitions when you get down start going down the rubber path, but it would be,
Yeah.
we called it terminal blend. Like for example, in the Tampa area, there would be a terminal contractor would send a tanker load of binder, and then the company would mix the rubber and the binder and drive it back to the asphalt plant. So all the
Yeah.
blending was done at these remote locations. None of it was done on we did it initially on project sites, but it became unmanageable. So we ultimately ended up going to terminals.
Yeah, and a couple of years ago, I visited a terminal in Massachusetts that had several tankers. They were bringing it on rail cars, the binder, and they were doing their own blending, and they were primarily using the rubber modified binders in preservation type of work, using the rubberized chip seals and so forth. So that's great. Anybody got some experience or discussion on using fog seals or penetrating rejuvenators to kind of repair their OGFCs? Nathan, I see you nodding a hair there.
Yeah, yeah. So I didn't have any data on here for it, but I know that this is something we've actually done on the test track before with some pretty good success. It's you know, the question is, can you do rejuvenating fog seals or just spray on rejuvenators without affecting permeability? That's really that's the main thing. And then how quickly does it take for skid resist or friction to come back?
Yeah.
And so the short answer is yes, that we have done that, and it can be done, and it does. You do not have to sacrifice long-term permeability for doing that. There's actually a lot of treatments nowadays that are just straight rejuvenator for this very purpose. And this is actually something that we intended. We have an OGFC section on the track for Alabama DOT right now that Chin and I have been working on doing this exact thing. So we hope to have some more recent data about the effects of spray-on rejuvenators on binder quality and friction and then permeability. But yes, you can do it, and it does work.
Great. There was some presentations I saw maybe about 10 years ago, and I'm not sure if they published a report, but Georgia DOT did some studying to see different application rates of fog seal to try to rejuvenate and keep their OGFCs healthy. But the presentations I saw were kind of based around how fast did the friction come back, and they tested daily for a week and weekly for a month and monthly for 6 months to see when they got that recovery, and they felt pretty comfortable with it. So I thought that was quite interesting. Go ahead.
A lot of really good comments to questions on here. Friend of the show, Todd Mansell, had some really good comments on heating up paving equipment. Todd's forgotten more about pavement construction than I'll ever know, so he's a great source on that.
Yes,
so thank you, Todd, for that. Joe LaRusso had a comment on War Mix, then I'll kick it back to you to moderate this. But War Mix technology on in OGFCs, and this is actually, we did this in the most recent test track build in 2024 for the Mississippi DOT, using local aggregate to Mississippi. We actually we ran it warm at the asphalt plant, paved it. I think it was behind this. It was actually, we had some trouble during construction, where we had some issues with the screed, and I think we were laying that at like 230 degrees, but we were still pretty happy with overall construction quality. So warm mix on OGFCs, it can work, and we've tried it with pretty good success.
Good.
Yeah, for the warm mixture, I want to add one thing there. There's some DOTs trying to use warm mixtures to replace fiber in the SMA and OGFC. And they're trying to, fiber, we use fiber trying to prevent the drain down, but some DOTs say, hey, do not use fiber, use warm mixtures. That in theory, that's like okay, but in the real life, there's a big trouble for the construction and put that for the construction and the transportation. There's a big pain for the truck driver to clean that. So but you have to be very careful to control temperature. Sometimes can cause you trouble. Even that, sometimes even you producing a low temperature, the drain down is still there because the high bond content for OGFC and SMA. Yes.
Yeah. Excellent. Excellent. Hey, Jim, one that I thought would be fun to come back and ask about with you real quick is how do you guys define the performance on here, like that limit? When did we lost performance? So is that mostly on the durability end, or is that mostly on the permeability end?
No, we don't, permeability is not a criteria that we monitor or anything like other than for research purposes. But no, we're looking at, the way Florida handles it is we provide a rating for rutting, ride, quality, as well as cracking. So raveling gets kind of incorporated into the crack rating. So we have a standard. So the pavement becomes deficient if any of those three cross our threshold. So that's how we do it. It contributes to a cracking deduction. And then if you get below, perfect pavement is a 10.0. And when we're down to the point we need to resurface is when it gets down, I think it's either a 6 or a 6.5, something to that effect. I know we probably have some pavement management guys online, but I think roughly a 6.5. So it just gets incorporated into the crack rating. What we do find is that sometimes there's a lag between when it becomes deficient and when it actually gets resurfaced. And with open graded mixes, that can be the nightmare scenario because, hey, now it's raveling and it's in our work program. We have a 5-year work program, but it's not going to hit the streets. We got another 2 years, so we're going to fix that project. So basically the maintenance folks hate these mixes generally for those reasons. So we actually have gone through, we've got some maintenance money and we'll go out and we'll do spot repairs to kind of slow down because again, especially if it's those joints, if every joint is raveling out on the project and they have a lot of joints, you have a lot of raveled area, or if it's a bad mix, sometimes it's the whole job raveling up and that could be a real nuisance to the public.
Yeah. Yeah, that's fun. So it's another friend of NCAT there, Greg Duncan, had mentioned about maintenance folks don't like the OGFCs, and there's Jim, even in Florida in the warm climates, they kind of struggle with it. And I think Todd Manziel even mentioned that as well. So
Travis, we had a meeting not long ago. DOTs were like all one big happy family, but we had a meeting not long ago with a bunch of maintenance folks, the director of maintenance. And honestly, I felt like they were looking at me out of the corner of their eyes. Like, you're the culprits why we have these raveling friction courses. And, it's funny. I do know a number of states in the Southeast have stopped using it because of the performance issues, because that's a real thing when you're breaking windshields and chipping paint. Raveling is a big issue with open graded friction courses, and it's unfortunate because it's such a good safety feature.
Sure. And that's what I think was really neat about some of the slides you had in your presentation on showing where those raveling locations were and how you guys are tracking and documenting. I thought that was really fantastic. Quickly, one or two more little things. Jim, you guys doing moisture susceptibility testing on your OGFCs?
No, we don't. What we do is we do require liquid anti-stripping additives. We have a pretty robust to get on our approved products list for a liquid anti-stripping additive. It has to run the gauntlet of about, I don't know, 6 or 7 different aggregate types. And so we don't actually test the mixtures. And somebody else had asked a question, I guess, kind of like, do we do any field checks? How do you know it's actually in the binder? And no, we used to years ago, back in the 80s, we used to have a little thing where we'd put, I don't know, like kerosene and some Ottawa sand and binder and shake it up, and it did something if it had the antistrip in it, something magical. But basically, so now, what we do is we require the material supplier, the binder supplier has to put it on the delivery ticket. And basically they're certifying that the material meets the DOT specs. So they have to use something, they have to use an anti-strip from the approved products list, and then they have to certify that they put it in the binder. We do not allow contractors to add it at the asphalt plant because, again, we're worried that how do we know it's actually in there? And we have a little bit more confidence with the suppliers, including the liquid anti-stripping additive.
Yeah. Yeah. Okay. Great. One little question came in right there about standard rolling procedures. I think the standard procedure is about hit it twice with the roller and get off of it, right?
Yeah, it's you're basically on all you're trying to do is seed it. Now it is
Yep.
I have wondered at times that if you went out and rolled it too much, you're probably going to reduce the permeability. Maybe you're going to improve the durability. I don't know. We
Okay.
do have with our South Florida limestone materials, sometimes they'll kind of break and you can over
Yeah.
roll them and it makes the
Yeah.
paper look bad and it reduces friction. So we do have a thing in there where if you start seeing broken aggregate, we limit it to a maximum drum weight of a certain pounds per lineal inch of drum
Yeah.
to try to
Yeah.
reduce some of the stresses so we're not breaking rock.
Okay. Yeah. And I've seen that on our test track as well. So, right. I'm going to close things up here. I appreciate everybody joining, and the discussion here at the end has been fantastic. We are way over our normal time that we end because that discussion was so good. Nathan, you got a
Travis,
couple extra slides?
I'll just
Yeah.
well, Travis, I'll just add. There's some questions we didn't get a chance to get to. Our email addresses are here on the slide before I change it. I'll give you guys a few seconds to jot them down, take a picture, write a note. We do regret we didn't get to all the questions, but it's a good problem to be 13 minutes over time and still have questions. So thank you so much for the engagement.
Right.
Thanks,
Right.
everyone. Yeah.
So our future webinars coming up on all sorts of things. We want to invite you to our website, ncat.us. There's all sorts of research on there that you can find. The recording of these webinars are there. We really like to share the training in your pocket. It's a YouTube channel. Please subscribe. It's free to get that kind of stuff. And we've got a new kind of sub-series on that we call Training in 90 Seconds. And they are fantastic. They're very quick little bites. There are all sorts of training opportunities. If you'll reach out to us, we can come to you. You can come to us. We can do all sorts of things when it comes to that. So some of our topics we've got coming up are things like the BMD implementation, some engineered RAS mixes that are kind of new that are coming out, but they're very cool. There's some longitudinal joint practices that we've tried on the test track and then seen go out into implementation other places that are really neat. And we want to hit this rubber discussion again. We have some great stuff there, especially with the dry processes coming out. And we have some sections on the test track that have used different additives that we've compared with each other. So given that, I'm going to close things out. Thank you very much, Chen and Jim, for your time and your expertise and fantastic presentations. And Nathan, as always, for making sure that you tie us into the track and everything that's been done there. Given that, I'll tell everybody goodbye.